We are going to be moving into the concept of gas laws next, and the important thing we should start with is pressure. Our objectives this lesson: we will define the property of pressure, we'll define and convert between various pressure units, we'll describe the operation of common tools to measure pressure, and we will calculate the pressure from manometer data. What is pressure? Pressure is force divided by area. That is a very lab-like way of looking at things. On a molecular level, how do gases exert pressure? Via collisions. Molecules collide with us, and the sum of the force from those collisions is the pressure we experience. Because molecules are constantly in motion, they can hit other molecules or you. The pressure is related to how many molecules hit us, how fast they're going when they hit us, and how heavy they are. A common experience that we have with pressure is atmospheric pressure. There is a relationship between atmospheric pressure and altitude. You can see this via these series of pictures at different elevations, that atmospheric pressure is dependent on elevation. The normal bottle, totally filled with air, is picture taken at 14,000 feet. The slightly squished bottle is at 9,000 feet, and the squished bottle is at sea level. The air around us pushes on us constantly. When we seal a bottle at a high elevation, by the time we get to the low elevation, it gets crushed. So at higher elevations, the atmospheric pressure is lower. When you go to lower elevations, the atmospheric pressure crushes the flexible walls of the bottle. Snazzy. The amount of gas molecules surrounding you is greater at lower elevations because gravity attracts small molecules to the large mass of the Earth. The further you go from the Earth, the fewer molecules there are trapped by Earth's gravity. There are just fewer molecules to collide with you at higher elevations, so the pressure that you experience goes down. There are many ways to measure pressure. A tire you buy from the store in the US might be labeled in pounds per square inch. If you look at the barometric pressure in the United States, it will be in inches of mercury. In the European Union, you would likely see it as millimeters of mercury, or torr, depending on where you are. If you're in Italy, probably torr. Same thing, different name. The SI unit of pressure is the Pascal, as previously stated. So if you want to get back and forth from pressure to energy or any other SI unit, you would want to use pascals. For the majority of the gas unit or the gas law unit, we will work with either atmospheres, ATM, or with millimeters of mercury / torr. They're the most common units used in this type of measurement. Whenever we have lots of different units, we often have unit conversions. So what if we want to convert between 1.5 ATM and pascals? I'll give you the unit conversion here. As with all unit conversions, we're going to use a dimensional analysis. We want to cancel out the thing that we don't want, and we want to keep the thing that we do want. So we're going to start with 1.5 atmospheres. We're going to put atmospheres in the denominator and pascals in the numerator. When we do that, we get 1.5 times 10 to the 5th pascals. Note that you can always flip the conversion factor and it will still be valid because it's a proportionality between different units. Okay, so now that we've got that out of the way, let's talk about ways to measure pressure. We measure atmospheric pressure with a barometer. We invert an evacuated graduated tube into a pool of non-volatile liquid and then submerge a portion of that tube and open it under the liquid. The pressure of the gases in the atmosphere pushes the surface of the pool of the liquid into the graduated tube. So the pressure exerted by the liquid due to gravity is called the hydrostatic pressure, which is equal to the height of the liquid times the density of the liquid times the force of gravity. When hydrostatic pressure equals atmospheric pressure, the level of the liquid will be stable. The difference in height between the surface of the pool and the liquid the surface of the pool of the liquid and the height of the fluid in the tube is the barometric pressure. So traditionally we used mercury. We now know that mercury is pretty toxic, so we don't use it for that purpose anymore, but we still use it as a standard. What fun. Many problems will be given to you in millimeters of mercury because of this. You could also measure it using a different, less toxic fluid like water, but if you notice in this diagram, the height difference of the mercury is much smaller than the height difference of the water. 760 millimeters versus 10,744 millimeters. So what causes this? The density of mercury is 13.1 grams per centimeter cubed, and the density of water is 1 gram per centimeter cubed. It's literally just the difference in the density. Now, it should be noted that we have moved beyond this technology for measuring pressure, and we can generally do this electronically, but the concepts are still really important to know. So, what else can we use to measure pressure? We can also measure pressure differences using manometers. I have a manometer in my basement to show that my radon remediation fan is operating successfully. Manometers are used for a variety of scenarios, and not all of them are lab-based. You can measure the pressure of a gas versus a vacuum in a closed-ended manometer over there on the left. In that case, the pressure of the gas is equal to height difference times the density times gravity. Now you can also measure the pressure of the gas in comparison to atmospheric pressure. The pressure of the atmosphere and the pressure of the gas will reach an equilibrium where the fluid in the manometer will have a height difference. In that case, you either add or subtract the height difference from the atmospheric pressure. Now I remember this by systemization. I don't actually remember those two different scenarios. So if you calculate the height difference as atmospheric end minus the gas end, then you can always consider it as pressure of gas is equal to pressure of atmospheres plus HPG, or the hydrostatic pressure. So when pressure of atmospheres is lower than pressure of gas, you get a negative delta H, and therefore you subtract your hydrostatic pressure. Memorize it in the way that you see fit. I'm going to show you how I do it with my method. The book will do it the other way. Use the one that works for you. In an open-ended manometer containing mercury, the height on the gas side is 13 centimeters and the height on the atmospheric side reads 6 centimeters. Atmospheric pressure is 765 millimeters of mercury. What is the pressure of the gas? So I'm going to do the pressure on the atmospheric side minus the pressure on the gas side. 6 minus 13 is negative 7 times 10 to convert to millimeters is negative 700 millimeters of mercury. And then I just take pressure of atmosphere plus negative 700, and that gives me 65 millimeters of mercury is the gas pressure. So I did that the way that I said that I would. It is this first scenario over here on the left. So we could have used it as that height difference, 13 minus 6 equals 7 times 10, and put it in there. Do whichever way you see fit, whatever works for you. All right, to summarize, pressure is force over area. Barometers measure atmospheric pressure, and manometers measure relative pressure or pressure differences. Hydrostatic pressure is equal to height times density times gravity. You can measure the pressure of a manometer by saying pressure of gas is equal to pressure of atmosphere plus the hydrostatic pressure. There are lots of units of pressure, and we have many different conversion factors. Just pick the one that you need for your particular application.